Okay, let's look at some practice problems. Yay! Well, we've seen this one already. So that is, we can have this pole cancel, and this 0 cancel with that pole, this 0 cancel with that pole, and so giving us this system. So we can go through and show then that this 0 canceling with this pole is making this pole uncontrollable. So our system loses controllability because this pole cancels with that 0. Okay, that's controllability. We can also show the system loses observability because this 0 cancels with that pole. So this pole is not controllable, not observable from the output. All right, so let's go through. So this is a state model for the system 1, second order. This state model for the second system, again second order. Both of these we can go through and show are controllable and observable. And one way to see that is because this is a diagonal system and I have no rows of 0, so that system is controllable, and no columns of 0 in the C matrix, so the system is observable. Similarly here, no rows of 0s in the B matrix, no columns of 0 in the C matrix. And so we can easily see the observability and controllability of both of these systems. Putting them now into the series interconnection, this is the state model that we would have. So combining B2 and C1, we get this quantity. D2, C1, so D2 is 0, so we get that. D2, D1 is 0. And so this is also 0. So this is the overall state model that we get. Okay, so I can go ahead and put this system. So this system is not in modal coordinates, but we can see, actually in this case, we can see the diagonals, the eigenvalues along the diagonal, and they're all simple and they're real. So we can diagonalize this system. So I go through and I put this system into diagonal form. This is the form that I get. And I can see that I get a row of 0s in the B matrix. And that row of 0s is associated with the eigenvalue minus 2. So we have lost controllability of this. We cannot control. So notice the input comes in, it cannot control that eigenvalue. Okay, so we've lost controllability. Similarly, we've lost observability. Okay, we've lost observability because I have a column of 0, so I cannot observe that eigenvalue. And so we had seen that, we kind of had that guess earlier, but in this case we actually see it come out. Now in this case we also have the condition that because we have single input, single output system, then some of those conditions that we looked at in terms of like the direction, it doesn't really matter. When you have a single input, single output system, the direction is not an issue. It's really it automatically comes out. So this is what happens. These are the modal coordinates, and so we can show that for lambda, we can show that for lambda is equal to minus 2. If we look at this vector, this left, this becomes a left eigenvector of the system, and it is associated with I think that should be 0 and 1. Yeah, it should be 0 and 1. So this eigenvector, if it's 0 and 1, we can show it's a left eigenvector, and that left eigenvector times this is 0. As a right eigenvector, this is an eigenvector associated with that eigenvalue, and multiplying this row times this column, I get 0. So we can see that, how that lines up. Okay, so it's just picking off that value. So remember, when you have a system in diagonal form, in modal form, the eigenvectors are columns of the identity matrix. So it's easy to find eigenvectors. Now, if we let lambda equal this quantity, we can go through and show that this is actually an invariant 0 of the remaining system. The remaining system has an invariant 0, and it's this quantity. Okay, so we have that. So this is the first example. Let's look at another example. Again, two systems in series. System 1, System 2. So this is single input, 2 output. Single input, 2 output. This system is 2 input, 1 output. So single input, 2 output, 2 input, single output systems. And we can go through and show also that in modal coordinates, we can put those systems into modal coordinates, and we can see that in fact they are minimal. If we go ahead and put the two systems into the series combination, this is what we get. Okay, so we have a 1 and all zeros. That looks pretty scary, and all these zeros and so forth. If we put this system now into modal coordinates, this is what we get. Again, we have a row of zeros, column of zeros. If we were to take this system now and form the overall controllability matrix, we would see, because we get this row of zeros, we get a row of zeros in the controllability matrix. Okay. Incidentally, we can also see here these two rows are actually identical to one another. Okay, so we see more stuff going on. I'm sorry, they're linearly dependent. So if I were to divide this column by 10 and this column by minus 15, these two columns would be equal to each other. If we were to form the observability matrix, this is what we would get. We get a column of zeros coming out. And also we can see that these two columns are linearly dependent on one another. If we were now to take the two matrices and multiply them together, wow, we get all zeros. That's pretty wild. So that's a pretty interesting situation. So if we look at the original systems, this system has no invariant zeros. This system has no invariant zeros. If we look at the transfer functions, this system has a transfer function given here. This system has a transfer function given here. So notice that these two transfer functions are basically, well, they're this way, GA and GB, which are they're multiples of each other. This transfer function has 2GA and minus 2GA, 2GB and minus 2GA. And so if we were to go through and multiply G2 times G1, we would actually get 0. Now, the reason we didn't get 0 earlier, so we get 0. We get 0. So yeah, you can have all kinds of interesting things happen in all of this. Multiply this out, we get 0. A 0 transfer function, which is what we would expect since we got these 0 Markov parameters. So it's kind of crazy, but that's what happened. So basically, a single 2 output single input system going into a 2 input single output system, we can, so even though these have no invariant zeros, they have the overall system basically has a blocking 0. All right, here's another example. I have a system, and the output is going into a differentiator, and that differentiator, then I'm going to look at the output. My overall output becomes the output of this derivative. Okay, so suppose the output of a single input, single output minimal system. So I'm assuming this is minimal, and I have a d that's 0. Suppose this is passed through a differentiator. Under what condition is this overall system now observable? Okay, so so my overall output is not the output of the system, it's the derivative of the output of the system. Okay, so how would we answer this question? Under what condition is the system observable? Or is the system automatically observable or not? Let's find out. So here's our state model for our system. X dot is equal to AX plus BU, Y is equal to CX. Z now is equal to Y dot. So it's the output of a differentiator. Y dot. Y dot is equal to C times X dot. X dot is equal to AX plus BU. So Z is equal to CAX plus CBU. And so we have two states. So notice we have X dot and we have Y dot. So X dot and Y dot. X dot is equal to AX plus BU. Y dot is equal to CAX plus CBU. So here's our overall state model. Notice this is a series interconnection. And so this is my new A matrix. This is my new B matrix. And now my new C matrix is the output here. So Z is equal to CAX plus CBU. CAX plus CBU. Okay, so we have this. So this is our new overall state model. And I'm looking here and I'm seeing these zeros coming out and I'm saying, that looks fishy. All right, well, let's check the overall let's check the overall observability matrix. So C bar, A bar, all the way down to C bar A to the power N. So A bar to the power K is given by this. And we can see that this then, so multiplying A by itself, take this, multiply it by itself, K times, I get this. And so I can go through and show that Q naught, the overall observability matrix, is given here, and notice I have that column of zeros. So basically this system will not be observable since there is an eigenvalue lambda equals 0 and a right eigenvector v not 0. So for example, if I choose a vector of this form where this is not 0, I can show that I get the same thing back. Or rather, if I set this equal to, I get this quantity. So notice that since lambda is 0, I have this relationship, and I also have this relationship. So this is my overall A matrix, this is my overall C matrix, and I have thus shown that the system is not observable. So we can analyze systems this way. So, and there are obviously a myriad of configurations we could consider, but this gives us an example of how to analyze a system in an unusual situation. So, for example, I have a transfer function. Here I have a state model which has a transfer function. The differentiator is actually a non-causal thing, and so I have a transfer function, but it's not a causal transfer function. And anyway, I can go through and show that my system is not observable. So we've only checked the observability. We could go through and check controllability, but I'll leave that to you. to check. Under what conditions is the system controllable? So again, we need a left eigenvector and so forth. So this is minimality and interconnection practice problems. Thanks for watching.